Welcome back to this channel for solutions of actuarial exam problems. We will look at an exam MLC problem today. My name is Krzysztof Ostaszewski. If you can't say my name, you can just call me Chris. And if you speak Polish, you can say my name. If you speak any Slavic language, you should be able to say my name. If you can't read it in Polish, just ask me. I'll write it for you in Cyrillic anytime. You can find information about me at smarturl.it/Jedi. I use this forwarding service smarturl.it, and then you pick a word that easily associates with what you want to tell and what you want in that website that you want it to go to. Well, Jedi is me. Although maybe, I don't know, maybe I should join the dark side. I'm friends with Darth Vader, as you know, and so I'm really confused about this whole thing. You can find my advice about how to pass actuarial exams and at smarturl.it/pass. And this YouTube channel is smarturl.it/pass actuarial exams. My exam MLC manual is at smarturl.it/btdt-MLC. And BTDT stands for been there, done that. That's what you need to be able to say every time you look at a problem on an actuarial exam. And you need to be able to know what to do to solve it, and solve it immediately, because you only have 5 to 6 minutes per problem. And if you're not prepared this way, then you're not prepared. You don't have time to think on the test. All the thinking has to be done before the test. You have to be so prepared that you know immediately what to do. Thinking is the last resort of the unprepared, and if you're unprepared, you will probably fail the test. And if you think that you are smart enough to not have to memorize things, then you're not really smart. So this is a serious and hard exam, and you need to study hard, and you need to know immediately what to do when you see a problem on the test. This is a problem from the exam MLC in spring of 2017, problem number 8 in multiple choice section. For a fully continuous whole life insurance of $100,000 on a 35-year-old, you are given the annual rate of premium is $926. Mortality follows the illustrative life table. Deaths are uniformly distributed over each year of age. Interest rate is 6%. Calculate the 75th percentile of the loss at issue random variable for this policy. One instinctive reaction that you should always have is when you see a problem with the words illustrative life table, you check the interest rate. If the interest rate is 6%, then it's the same as in the table, which means that you can use all the values for life insurance and life annuities for the calculations. And if it's not 6%, well, that's a standard trick. Doesn't happen all the time, but it happens from time to time, and then you can only use the values of probabilities, probability of dying, probability of living, and the size of the population. But all the actuarial present values of annuities, life insurance, so on, are calculated in that table, assuming the interest rate of 6%. So you always want to check that, and here it is, 6%. The loss at issue random variable for this policy is $100,000 paid at the moment of death, so it's present value of the death benefit, minus the premium that the company receives as a continuous life annuity, which is 926 A bar angle T. Okay, but A bar angle T is 1 minus v to the t over delta. Delta is the natural logarithm 1.06, and 1 minus v to the t is 1 minus 1.06 to the minus t. So we calculate the numbers that we have there, and this ends up being, if you combine the terms that have 1.06 to the negative t or minus t in them and the numbers, this ends up looking like this. It's 115,891.837 times 1.06 to a minus t minus 15,891.837. We are looking for a number, and I didn't want to write L 0.75 because L stands for the population size. So I just use lambda, not that lambda looks similar to big L, it doesn't really, but I just felt more comfortable with this. But we are looking for the 75th percentile of that probability distribution, so I'm going to denote it by lambda 0.75, and probability that L is less than lambda 0.75 is 0.75, and L has that form that we just derived. Well, then that means that we must have 0.75 equal to the probability that this formula for L that we found in terms of t, that this whole thing is less than lambda 0.75. So we rearrange the terms so that we only have the expression with t in it on one side and the rest on the other side. And t is in the exponent, and remember the simple rule: if you see the unknown in the exponent, you're going to be taking natural logarithm. So you take natural logarithm of both sides. We end up with minus t times ln of 1.06 less than ln of this entire expression there. So we divide both sides by minus ln of 1.06, which is a negative number. That switches the direction of the inequality and becomes probability that t is greater than this whole expression. Complicated thing, but this is what? The probability that t is greater than that number, right? And that's 0.75, and that's a probability. So really it is the 25th percentile of t. Oh, it's the time t such that of the original size of the population when the policy was issued, we still have 75% of people left. That's basically what this says. Okay, let's denote t.25. Let this be the 25th percentile of the distribution of t. So probability that t is less than or equal to t.25. That's actually 1 minus the population size at age 35 plus t.25 divided by L35. That's equal to 0.25. So as I said, we really could have intuitively argued this, that the population size at age 35 plus t.25 has to be 75% of the population size at age 35. But we have that population from the illustrative life table, so the population size at the age that we're looking at has to be 7,065,492.75. And in the illustrative life table, that number lies between the population size at age 68 and 67. And we are told in the problem that uniform distribution of deaths within the year of death applies. And that really means that we can use linear approximation between L68 and 67 to find the value of that age that we're looking for. And we basically say that the fraction of the interval between the population sizes is the same as the fraction of the interval between the ages. That's what this ratio here says. Well, then t.25 has to be this 32 comes from 67 minus 35 plus the ratio of these population sizes that we have on the left hand side. In the right hand side, 68 minus 67 is just 1. And so we really have there t.25 minus 32. 32 moves to the other side, and we get this. So this is 32.743122 and so on. And that has to be that whole expression that we had with lambda 0.75 in it. That has to be equal to this number. So we just now solve for lambda 0.75. Comes out to be 1305.4445, and that's answer E, and we are done. Please remember this is copyrighted material, and exercises and problems from Society of Actuaries are their property, used here with permission. Good luck on the exam. Good luck in your studies.